Welcome. In this video I'm going to go over the solutions for problem set 10.2 parts C and D, which looks at the reactions primarily of alcohols and then a few other odds and ends, but mostly the alcohols. Number 13a says write equations for the complete combustion of ethanol and propanol. So ethanol, you have to realize, is minus E, so it's 2 carbons. So it's going to be C2H5OH, making it an alcohol. It's still going to combust with oxygen and give you CO2 and H2O. And then it's just a matter of balancing the equation. So if I put a 2 here and a 3 here, that gives me 4, 7 oxygen, but I've got 1 over here in the alcohol, so a 3 here will balance it. And then for propanol, mice eat peanut butter, so this one's going to be C3H7OH, or you can write the CH3, CH2, you can write out that way as well if you'd prefer. But C3H7OH, again with O2, is going to give you CO2 and H2O. And balancing it, I'll need a 3 for the carbon, I'll need a 4 for the hydrogen, and now I have 6, 10 oxygen, which out of the 10 oxygen, 1 is being used by the alcohol, so that would leave me with a 4.5 here, or if you prefer, you could double it to 2, 9, 6, and 8. And again, IB doesn't care if you use halves to balance because we're talking molar amounts really. Part B, the esterification reaction between propanoic acid and butanol. So propanoic acid, mice eat peanut, so that's 3 of them. So I could write this CH3, CH2, and then the acid is the COOH group. And then with butanol, that's going to be 4 carbons and then 9 hydrogen with the OH group. And what you have to remember is that you're going to snip off the OH and the H, or the OH and H the other way, but that's where you take off and you're going to combine these two. So when these combine, it's going to be the oxygens in the middle combining them. So I can write the CH3, CH2, COO, CH2 3 times, CH3, I can write it like that. Or I could go ahead and write the whole thing combined to C2, H5, COO, C4, H9. Either one is fine. I think the first one's a little easier to see what you have there, but you're going to end up with that plus water. It's a dehydration reaction. And as far as what you would name this, to name this, you name the alcohol first, and that becomes butyl instead of butanol. And then the propanoic acid becomes propanoate. So that would be the ester I've produced, is butyl propanoate, and either of these structural formulas works for that. Number 14 is looking at oxidizing different alcohols. So 14a wants to know what you would predict would happen with 2-butanol. So I've got my 4 carbons, and it's telling me my OH is off of the second one. So if I oxidize this, I'm going to end up with an oxygen like so. And so the product of that is going to be a ketone. So this is going to be 2-butanol. Or it could be written as so. And I guess actually all they asked for is what's going to be produced. It's going to produce a ketone. Would be the correct answer. And what color change would be observed? With the potassium dichromate, you always go from orange to green. And then B, your product, you have methanol, and the product is collected by distillation immediately. So with methanol, there's only one place, there's only one carbon for that oxygen to be on. So this is going to become like so. So this is going to be considered an aldehyde. And my color change again is going to be orange to green. For letter C, I have 2-methyl-2-butanol. So I still have the 4 carbons, but this time I have the second carbon has got the OH group on it, and it's also got 2 methyl groups on it, which look like this. So this is a tertiary alcohol, and there's going to be no reaction because there's no room to get into that OH group and oxidize it. Number 15, explain what is meant by a nucleophilic substitution using the reaction between NaOH and chloroethane to illustrate your answer. So chloroethane, I've got C, I've got my H's, and I've got a chlorine. And this chlorine tends to pull the electrons that way. I'll put my H's on so you can tell I actually mean a negative charge there, leaving the carbon end positively charged and wanting electrons. So the carbon is what we call an electrophile. It needs electrons. So if you remember, phile is like attraction, and I hate to say it, but pedophile is an attraction to peds or children. So an electrophile is an attraction for electrons. So carbon's wanting the electrons, the chlorine's holding them, but with NaOH, OH is so polar, this is actually a stronger nucleophile which is stronger than the chlorine. So the OH is able to bump off the chlorine, and that's considered a nucleophilic substitution because this nucleophile substitutes for another nucleophile. It's a lot of fancy words for what we did in HP. It's just a matter of the electronegativity or the polarity of it, but it's able to bump it off. So then my products would be, I would end up with my, I guess I can write CH3, CH2, and then I'm going to have the OH at the end here, which is then going to leave me NaCl as my other product. Number 16, discuss why benzene, which is highly unsaturated, tends to undergo substitution reactions rather than addition. So with benzene, if we draw out the hexagon, it appears to have 3 double bonds, and typically with alkenes, those double bonds are easily broken. But because these are actually 3 delocalized pairs of electrons which actually rotate or resonate between all 6 places, it tends to behave more like an alkane. So it's because of the delocalized electrons in the double bonds, means this is far less reactive than a typical double bond. So it's going to behave more like the alkanes, much less reactive single bonds. Question number 1 says, which reaction type is typical for a halogenoalkane? So you already have the halogenoalkane, like so, like chloromethane here. And so they want to know, well, I don't need the UV light, but what I have to know is that my carbon is going to become an electrophile because the chlorine, this is such a polar bond that this becomes a nucleophile. So I end up with a nucleophilic substitution when this gets bumped off and replaced by something like hydroxide. So nucleophilic substitution is the one we're looking for there. Which I guess you could narrow it down because you know with an alkane it should be a substitution and not an addition reaction. And then you'll just have to remember that the carbon is the electrophile, so the carbon stays there and it's the nucleophile that gets substituted. Number 3 takes you through this is what we call a pathway. It's a series of reactions that take you from this halogenoalkane to an ester at the end. Unfortunately, you're not being asked to name them, but you're just supposed to tell the correct order of the reaction types. Well, on the first one, if I look C3H7Br and then C3H7OH, the only difference is the Br becomes OH, so that's a simple substitution. So B and C are out of the running because that one, everyone should be able to tell, is just a substitution. Then it becomes C2H5COOH. That's not a simple substitution anymore. But my only choice is oxidation for both A and D, and that is what it is. It's an alcohol being oxidized. And then the H group is broken off, and this group is added on. So when I've got the COO group between two different R groups, that's an ester, and esterifications happen with water being squeezed out, or they're called condensation reactions. So that would be A. And that one you should be able to reason out, because you should be able to tell that's not considered just a substitution when you put the whole C2H5 group in there. That's a little more complex. Number 4, which reactions could be used to form the compound below? So again, I have to look at what I have, and I see that this is an ester. So I've got this group here, and I've got this group here. So what I have to figure out is which one is my acid and which one's my alcohol. Well, my acid has to be the one with both oxygens attached to it. My alcohol only has the one oxygen. So my alcohol just has 2 carbons, so ethanol is what I'm using. So A and B is possible. And then I have to count up. I've got 1, 2, 3, 4. I've got 4 carbons, making that a butanoic acid. So 4A would be my correct choice. Number 7 says, which conditions are required to obtain a good yield of carboxylic acid when ethanol is oxidized using potassium dichromate? So what you need to realize is ethanol will become an aldehyde first, and to get the carboxylic acid, you have to keep it in the container, or what we call reflux. So 2, heat the reaction mixture under reflux. I definitely need that. So then 3 doesn't make any sense. Distill the product as the oxidizing agent is used. Reflux and distillation are 2 opposite things. Reflux means you're leaving it in there. Distillation means you're taking it out. So for sure it's 2, and it's definitely not 3. So I don't even have to know if I need to add sulfuric acid or not. A is my only logical choice. Number 9, when propanol 1 is heated with acidified potassium dichromate, so mice eat peanut, I've got 3 carbons with an OH group on the first carbon. The others are hydrogens. By the way, IB will expect you to draw in the hydrogens. That's just me being lady. See? When it's heated with potassium dichromate and reflux, so that means it's going to go to be in the aldehyde, and then it's going to go a step further and become the carboxylic acid. So I would expect it to be CH3, CH2, COOH. I'd expect it to be a carboxylic acid, and it would be C. It can't magically come up with 4 carbons there when you only started with 3. 16A looks overwhelming, but take a deep breath and you'll see that it's actually quite doable. 2 compounds A and D each have the formula C4H9Cl. And then they tell you what happens when each one is reacted. Well, there's really 3 possibilities here, because I can have carbon, I can have my 4 carbons with the chlorine in a primary position, just attached to 1 carbon. Or I can have my chlorine attached to the second one and become a secondary halogenoalkane. Or because of because it's a butane group, I could have a tertiary with CH3 methyls attached to all of it, and then the chlorine here. So it says compound A is reacted with dilute aqueous sodium hydroxide to produce compound B with the formula of C4H10. Compound B is then oxidized with acidified potassium manganate to produce compound C with the formula of C4H8O, and then it resists further oxidation. Well, this one I would expect to undergo 3. I would expect to become OH, and then it could become an aldehyde, and then it could become a carboxylic acid. So this apparently is neither of the structures. So compound A to become B is going to look like so. So this is apparently A, and then B becomes the alcohol. And then upon further heating, it's going to become, is that C? C is going to become a ketone. And then cannot become a carboxylic acid because there's no more hydrogens readily available, which means this hydrogen doesn't belong there. So that's the sequence of A, B, and C. This one over here then must be D. It must be a tertiary alkane. And you can go ahead and get it to react with the sodium hydroxide, and I can get this to become a tertiary alcohol. So I'd have CH3C, CH3, CH3, and my OH, and that would be E. And that's as much reacting as I'm going to get from a tertiary halogenoalkane. And then B says, deduce an equation for the reaction between propanoic acid and methanol, identify the catalyst, and state the name of the organic compound X formed. So let me just pause and move this up a little. So propanoic acid, mice eat peanut butter. So I've got this is part B here. Grab my pen again. So it's going to be CH3, CH2, COOH. There's my propanoic acid. And then methanol is just going to be CH3OH. And they want to know, state the name of the organic compound X formed. So when these two combine, I'm going to end up with CH3, CH2, COO, CH3, and H2O. So my organic compound is the big one, the ester, not just the H2O. So then my catalyst is going to be concentrated H2SO4. And as far as the name of it, I named the alcohol first, and that's become methyl. And then this is going to become, it's the propane group, so propanoic would be the name. So 17, again, looks a little overwhelming, but choose your way through it. You should be able to do some of this. In fact, as you read through A and they talk about the reaction, describe the color change. That should be orange to green. Deduce the oxidation number of chromium in Cr2O7 2-. So again, that should be a fairly easy one. I've got 7 oxygen at a -14, 7 times -2. And then I've got the 2 chromium are each going to have to be +6. So that should be doable as well. So you've got the first 2 of the 6 marks, which is a great start. And then C, state the balanced half equation for the reduction of dichromate ions to chromate 3 ions. So I'm going to start with Cr2O7, this is part C, Cr2O7 with a 2-. And it's becoming Cr3+. So I'm going to have to put 2 here to balance it. And then I'm going to need 7H2O over here, which means I'm going to need 14H+ over here. And then finally, when I look at my charges, I've got +6 on this side. Over here, I've got a net +12, so I need 6 electrons, and that would be my half equation for C. D says deduce the half equation for the oxidation of ethanol to ethanol, and hence the overall redox equation for the oxidation. So D, I'm going to have CH3, CH2OH is going to become, just need an arrow here, is going to become CH3CHO, and so I'm going to need 2 hydrogen to balance that, which means I'll need 2 electrons. So then I'm going to have to multiply this by 3 before I can combine them, so that I have 6 electrons. And when I go ahead and add these up, then I'm going to come up with Cr2O7, 2 minus, plus 3CH3, CH2OH is going to yield, plus 8 hydrogen, can't forget those, that's the net, 14 and 6. And then that's going to yield the 2 chromium ions, plus 3 CH3 CHO, plus 7 water. And E wants to know why it's necessary to carry out the reaction under acidic conditions. That's because the H plus is needed to balance. It's needed to help facilitate that electron transfer. And F says, identify the organic product formed if excess potassium dichromate is used and the reaction is carried out under reflux. So under reflux, this will become a carboxylic acid, and it's going to become a carboxylic acid with just 2 carbons on it. So this becomes CH3COOH under reflux. And it says identify it, so I imagine you can either write the formula or you could give the name of ethanoic acid.